Is Leopold's 155th birthday. No one has mentioned that so far. It's an auspicious day. I may disappoint the organizers, so I suspect that I was invited here because in the past I've done a substantial amount of work in vortex dynamics and locomotion problems, but I thought it would be interesting to talk about something different from the things that I usually do. So my topic for today is a topic about which I know only a little bit. So the results that I present will be preliminary results, but then perhaps I can get feedback from you on how to make these results stronger results. I have several collaborators. So some of what you see today I will show in the beginning some pictures and movies of physical experiments. So those physical experiments are done by a graduate student named Stephen Howard at the University of North Carolina, and his PhD advisor is Stuart Smith. So I rely on them to provide me with physical things. And then in the second part of the talk, I'll show some computational results. And so the computational fluid dynamics work, the simulations are done by a PhD student named Kwitae Chong, who's at the University of California, and his PhD advisor is Eldredge. And given that these two people are involved, one might wonder what I do, and I think it was just sort of my idea to pull all of these things together. So the basic idea of my talk is as follows. Imagine that you have a bounded fluid, and you vary the shape of the boundary of the fluid periodically in time. In general, it is not the case that particles suspended in such a fluid will execute periodic motions. Although the boundary motion might be periodic, the motion of tagged fluid particles or solid particles suspended in a fluid will in general not be periodic. This is something that's true even in the simplest cases. So for example, even in the situation where you imagine an inviscid irrotational flow, so an ideal fluid, and the particles that interest you are infinitesimally small, neutrally buoyant, so have the same density as the fluid, it's still the case that if you vibrate the boundaries of a fluid, the fluid particles may not execute closed bands. So this is a famous problem. It was known to Stokes, pictured here. I found this movie on Wikipedia this morning, so it's not my movie, but it's a nice illustration of this. So Stokes discovered this phenomenon in the 1840s. He was modeling the problem of fluid particle motion in the presence of traveling surface waves. So when I play this movie, what you'll see is the surface of the water will deform in a way that corresponds to translating waves on the top. And then these lighter dots are tagged fluid particles. And the movie doesn't complete a full cycle. But you can see the paths followed by fluid particles. And it's not difficult to imagine that at the conclusion of one wave motion, these particles will not have come back to their starting points. So that discrepancy is frequently called Stokes Drift. And it's well understood in this case in which the flow is ideal. However, it's easy to complicate this problem. So for example, if one considers a viscous fluid, so at some finite non-zero Reynolds number, then the fluid dynamics become much more complicated. One can complicate this problem by imagining that the particles to be traced are not actual fluid particles, but are solid particles that might have density different from that of the fluid. So there are variations on this that make this a harder problem, and I want to talk about some of those variations. This is an important problem. It arises in nature. So here's a movie that I will show you of a microorganism called Verticella. So this is a light microscope movie. So this creature is just about the smallest size that you can see. And here's a cartoon illustration. So the idea is that this organism has a tether, anchors itself in place to some surface, then has a body with a mouth at this end. And although you can't see it in the movie, surrounding the mouth are these system of vortices, right? The vortices oscillate in a way that's synchronized. So if I play the movie, what you can see is as a result of the motion of the vortices, there's this circulating cell in the fluid. The focus is changing. You can also, if you look closely, see that there's another one here.
Is this about real time?
That is real time, yeah, that's right. And so, in fact, this thing has a radial symmetry, so these vortices are going in all directions.
Cilia or vortices?
So it's I'm sorry, what was the question?
Cilia or vortices? The actual thing that's moving is the actual animal that's moving, right?
No, the animal is anchored in place.
No, I mean
It's the cilia. So there's this.
Yeah, but you say it's the cilia that are moving that generate vortices. The animal is not made of vortices. So
That's right. Yes, the animal is not made of vortices. The motion of the cilia creates this toroidal structure that you see in cross-section here in the movie in Kwitae. All right, so sort of this donut-shaped structure with this circulation itself. So the idea is that you know, in the fluid, the reason you can see this in the movie is there are particles suspended in the fluid, and this is how the animal feeds. So it brings fluid around and into its mouth from all directions. If you look carefully, you can see that beyond this circulating cell, there's actually a counter-rotating cell here, and that'll be significant in some of the discussion later. Yeah?
Sorry, I'm not sure if I fully understood the picture.
Sure.
Where is the cilia and how these vortices are being formed?
So this is the mouth of the organism. So surrounding the mouth of this organism, pick the organism up and put it here, are these cilia. So these cilia oscillate in probably that way, and it causes this circulatory flow. Does that clarify?
And what's the size of this organism?
At the limit of visible with the naked eye. So micrometers in size. So my interest in this problem began when I saw that a colleague of mine had a physical system that was very similar, at least qualitative, to this system. So you may be familiar with atomic force microscopy. So if I have a surface and I want to measure the texture of the surface, one way that I can do that on a very small scale is I can take a probe on the order of microns, and I can drag that probe across the table. And if the surface has texture, then the probe will bounce up and down as I drag. And so by measuring the deflection of the probe, I can get a measurement of the surface texture. So a variation of that is that people do dynamic atomic force microscopy, where you take a probe and you bounce the probe along the surface. You bounce the probe and move it along the surface. You can infer from the dynamics of the probe as you drive it what the surface texture is. So I have a friend who makes these probes. Here's a picture of one. So this is compared with a US coin. This is compared with a human hair in thickness. So this is the probe. So the probe is smaller than a human hair in thickness. And we see in these pictures it's attached to a tuning fork. So this metal object here is something that can be caused to vibrate at a certain resonant frequency. And so if you vibrate this tuning fork, then this probe will oscillate up and down. So he makes these probes to do this microscopy. But if you stick the probe in a fluid, in fact, you can create vortices such as we saw in the last movie. So here's a movie down in the corner here. You can see, here's the probe. And the probe is being induced to vibrate this way. And suspended in the fluid are small glass beads on the order of 20 micrometers. And so as this probe vibrates, you can sort of see the glass beads on this side oscillate in this way, and glass beads on this side oscillate in that way. So they speed up and slow down as we play with the frequency of this. But essentially that's recreating in a planar cross-section the phenomenon that the Verticella on the previous slides we did with the radial symmetry. So what my colleague who made these probes now does with this is actually sort of interesting.
The frequency of vibration then?
Tens of thousands of hertz. And in fact, we're not turning it off and on. We're sweeping through a range of frequencies, but the amplitude of the motion of the probe varies according to the resonant modes. So the particles move more when it moves faster, and less when it moves, it has a larger excursion. What he now uses these things for is for polishing. So if you've got a very brittle surface, and one that you want to polish smooth without actually touching it with a tool because you might crack the surface, what you can do is you can make a slurry of abrasive particles like this, put a layer of this fluid with particles suspended on the material, and then put the stirring rods in, and then this will create these vortices, and the vortices will polish the surface. So it's vortex machine. This is actually one of 2 experiments then that we have of this nature. So, as I said to Andy a moment ago, so in this movie you're seeing a probe that's on the scale of micrometers across, oscillating in multiple tens of kilohertz. We have a larger, slower experiment as well. So we also have a device currently in construction where we have a millimeter thickness, a fraction of a millimeter thickness probe that we want to oscillate between, up to 10 kilohertz. And sort of look at these 2 problems complementary. I don't have a movie showing this apparatus driving particles in fluid, but I'll just show you the technology because it's different. So we build this sort of aluminum object called a flexure. So this thing is about this big, and we have a piezoelectric actuator here. So we send a current to this, it expands and contracts, and so in so doing, it's able to drive the position of that point vertically fairly precisely. So we've got good control over vibrations of this tip. So we glue to that tip, coming out of the plane of the board, a probe that can then be put down in a fluid. All right, I have an entertaining illustration of the control we have over this thing. So one can plug an iPod into it and play music. So here's just an audio recording I did. I drove this device with my iPod, and then using the microphone on my phone, I recorded the sound. So just to demonstrate that we have good fidelity up to about 10 kilohertz, and that this device vibrating in the room reproduces Led Zeppelin reasonably accurately. So it turns out that controlling a system like this is not a trivial engineering problem, but it's the PhD student's problem. So our goal then in this area is to see if we can adapt this technology to create systems for contact-free manipulation of small objects suspended in fluids. There are plenty of biological applications for this sort of thing. Perhaps you've got a cell suspended in water and you want to reorient the cell, manipulate the cell, a strand of DNA, so a macromolecule. People have reasons to want to play with these things, but they break when you touch them with physical tweezers. Right? There are particle sorting applications. I might have a suspension of mixed small and large particles, and I'd like to be able to sort them according to size, for example, according to density. So our goal is to create a system using several cilia of this kind, and then figure out enough about the fluid mechanics so that we know how to control multiple cilia in parallel to achieve reorientation, sorting, and so forth of particles. So I'll comment that in both of these experiments, the Reynolds number is relatively low, so order of 10 to 100%. It's not significant. So now let me talk about mathematical modeling a little bit. So my background is actually in theoretical mechanics, analytical mechanics, geometric methods of mechanics. So for me, I want everything to be a Lagrangian system or a Hamiltonian system. So the starting point for creating a mathematical model for a system like this, which will be an idealized mathematical model, is to think about the structure of the phase space in which the dynamics evolve. So depending on your religious affiliation, that'll typically be the tangent bundle or cotangent bundle of some sort of configuration space. It turns out that the space of configurations for a system like this, a general system in which you've got a deforming boundary fluid that moves within the bounded region, has a nice mathematical structure to it. So if you imagine, first of all, in specifying a configuration of a system like this, I want to specify the shape of the boundary. I can imagine that all possible boundary shapes correspond to distinct points in some manifold represented here in green, so that if I periodically vary the shape of the boundary, that corresponds to executing some sort of closed curve in the space of all possible boundary shapes. And then, corresponding to each possible boundary shape, I have all possible arrangements of fluid particles, right? So there's this fiber bundle structure that's present, whereby I imagine that corresponding to each point in this green manifold of boundary shapes, there's a fiber points in which correspond to all the ways that I can rearrange the fluid particles. I won't delve deeply into this picture because it might not be familiar to everyone in the room, but I'll remark that there are different ways that one can think about this problem. So one can imagine wanting to control the entirety of a bounded fluid, such that the configuration of that fluid corresponds to, say, some smooth map of diffeomorphism from a reference configuration. In that context, one has a group structure on the fibers in this picture, and so this bundle might be what's called a principal fiber bundle, where you've got a lead group structure on the fibers. It might instead be that you're interested only in tracking the location of some finite number of particles in the fluid, and so you don't really want this infinite dimensional group. Instead, you want to imagine that, well, every time you complete a loop in the boundary shape space, you're just mapping n particles from points in the plane or points in R3 to other points. So in that situation, one thinks in terms of this fiber corresponding to symplectic maps on the space where the fluid particles live. So there are variations on this. So perhaps this is a principal bundle, perhaps this is symplectic. The flow physics, though, let me talk a little bit about the physics. So I want to preserve this bundle concept just for a couple of slides. So in certain extreme cases, this problem has a very simple mathematical structure. So for instance, if I assume, I've said that my experiment is a low Reynolds number experiment, relatively low Reynolds number experiment. If I imagine that I'm in the extreme of 0 Reynolds number, so absolute Stokes flow, so that's a magical extreme in which all inertial phenomena in the fluid are completely overwhelmed by dissipative phenomena, by viscous phenomena. That's sort of the definition of Stokes flow. Equivalent to that is the statement that if I move the boundary of a fluid at the extreme of low Reynolds number, then the fluid particles will move in a way that is determined entirely by the motion of the boundary, but in a way that's independent of time parameterization. So if I move the boundary in this way, and the fluid particles move like this, these trajectories would be the same whether I did that over the course of 1 day, or 1 year, or 1 second. So this independence of time parameterization is equivalent to saying that if I have an initial configuration for my boundary and for my fluid that projects onto a particular initial shape of my boundary, and then I execute a cyclic change in the shape of the boundary, the way in which the configuration of the entire system will evolve to a final configuration, which is also the same boundary shape, is entirely determined by the geometry of this path, and not at all by the time parameterization. I could execute this path half quickly and then half slowly, or the other way around, and I would get this sort of same change in fluid configuration. So in that sense, this problem fits into the category of problems involving what's known as geometric phase. So a construction like this that allows lifting of trajectories in this purely geometric way is called a connection. And one can think of changes in fluid configuration in situations like this as corresponding to what are known as geometric phases, or holonomy, so this is actually, this sort of structure arises in a lot of locomotion problems. Locomotion of the Reynolds number problems, for example, which I worked on quite a lot, developed this picture years ago. So the reason one wants to look at problems in this way is by modeling the physics in terms of this connection object. The connection gives you a tangible thing that one can use, for example, to design control techniques for systems like this. So I have a conference paper from a couple of years ago that looks at the problem of moving in a very simple way the boundaries. Imagine I've got a fluid with just a single stirrer in it, and I can move that stirrer in the plane. So planar fluid, I move the stirrer in some way, and I want to induce motion in a single particle of fluid by moving the stirrer. So one can formulate that problem in terms of the connection in this way at the limit of Stokes flow, and then design control laws by doing some analysis of this connection. I'll show you some cartoons from that paper, but let me talk not about the Stokes flow extreme. I want to point out that, in fact, this same simplification occurs for different physical reasons at the extreme of ideal flow. So in an inviscid irrotational flow, it is also the case that if you move the boundary, then the way in which the fluid moves as a result is independent of the time parameterization of the boundary motion. And, as a corollary, if I begin moving the boundary of an inviscid fluid and then I stop suddenly moving the boundary, the fluid will immediately be arrested, right? So there's no, although there's no dissipation in this case, and this is essentially potential flow that I'm talking about, because one can solve Laplace's equation and obtain the fluid flow uniquely from the boundary motion. It's the case in ideal flow as it was in Stokes flow. There's no way for the fluid to build up momentum and then evolve dynamically after the boundary motion stops. Right, so here's an example. So suppose in a planar ideal flow, I have a circular cylinder. So this is a solid object. And as a control input to this problem, I can move this solid object around the plane any way I want. Now, inside this little box, I've taken a little bit of red dye and I've tagged one particle. This box explodes just so you can see it more clearly into this box. So this is a close-up of this box. If I execute a cyclic motion in the position of that circular cylinder, then the motion of that fluid particle will describe some path that is, as I said at the beginning of the talk, in general not closed. So this non-closure of this path, this is the Stokes drift that arises. So it's the boundary executed a periodic change, but fluid particles execute a non-periodic change. So
those arcs or circles?
Those are in fact arcs and circles. Yes, I think they are. So the shaped manifold in this problem, the green manifold from the previous cartoon, in this case is R2. Right? So the configuration of boundaries is parameterized entirely by the position in the plane of this cylinder. So I've just got these two real parameters that I use as control points. I claimed, I would show you, that if one, in ideal flow, you can work through the math for this problem explicitly, but if you work out what the connection for this system is, you can use that to design, for example, a controller to do particle attraction in an intuitive way. So the last movie I showed, this went in a perfect square, and this particle moved in some way. Here's a different shape, a different sequence of boundary shape changes. So if instead of moving in a square, what I do with this cylinder is I move it first along an arc that is always perpendicular to the instantaneous line between the cylinder and the fluid particle, and then I move directly toward the fluid particle, and then I retreat along an arc which is again perpendicular to the line joining the cylinder and the particle, and then I close that loop. So in this case, the Stokes drift amounts to moving this particle inward toward the midline of the system and slightly closer to the cylinder. So if you wanted to attract the particle to the cylinder, what you could do is you could repetitively execute this loop in the position of the cylinder and its mirror image. And so stroboscopically, I'm just going to show several frames in sequence that depict the position of the particle as I move this circular cylinder in a sequence of paths like that. So with each execution, the particle steps closer and closer, and I can draw the particle into the cylinder. So it's possible, both in Stokes flow and in ideal flow, to design feedback controllers that generate paths like this that either push particles away or attract particles. So that's sort of the preliminary work. But this obviously is a poor model for the cilia that I showed in the actual experimental piece. So let me talk for the remainder of my time about how one can try to model the more difficult circumstances under which, number one, the flow is not assumed to be inviscid or Stokes flow, and number two, where the fluid particles themselves, or excuse me, the particles that one wants to manipulate are not necessarily fluid particles, but are particles that might have finite size and or density different from the fluid. So the cheat that we adopt in doing this, so of course the fluid dynamics are complicated, right? If I've got the Navier-Stokes equations governing the motion of a massy solid particle suspended in a fluid, and I'm moving the boundary. Well, the coupling, if influence of the particle on the fluid complicates things significantly. So one way that one can approach that is to say, well, first what I'll do is I'll figure out how the fluid moves as a result of my prescribed boundary control, as if there were no particles present in the fluid. And then I'll compute the motion of a particle as if it were being pushed by that flow without influencing that flow. So my algorithm for studying this problem will be, first I'll show some examples. First I'll compute a flow field having to do with a particular pre-specified boundary motion. And then I'll imagine that flow field is now written in stone, but I can place a particle in the flow and have it evolve according to the forces that it would experience as a result of that flow. So this is a standard thing to do, and variations on the ODE to be used for a particle being driven by a flow like this go back to the 19th century. Which is a reasonably famous paper by Maxey and Riley in which they select a particular set of forces to do this. So these are the ODEs that I use to track particle positions. I won't tell you what all the symbols mean. Essentially, the symbol W is the vector velocity of a solid particle, small solid particle, relative to the fluid at the particle's location. This is the mass of the particle, this is the mass of the fluid it displaces, and the terms in this model include, well, effective mass, Stokes drag, this just has to do with the fluid force, the fact that the fluid velocity field is changing over time. This is an artifact of the fact that I've mixed W's and U's, U is the fluid velocity field. This is what's called the Bassett force. So this is somewhat significant in this work that we're doing, because in treatments of this problem in the past, this Bassett force, which has to do with sort of boundary layer vorticity shedding as a result of the fact that the particle is accelerating, this is computationally difficult to deal with, right? It's often called the memory term in these equations because it requires that one sort of integrate the cumulative effect of sort of vorticity diffusion from backwards in time all the way. So if you look back in the history of these problems, this term is often thrown out because it's inconvenient, but what we found in our simulations is that it's actually a significant term in those problems. So the two example systems for which I'll show you computational results are as follows. One will be, I'm going to assume that I've got a circular cylinder as you saw in the ideal flow case, but I'm only going to oscillate the circular cylinder back and forth along the horizontal axis. And I'm going to assume that the amplitude of oscillation is much smaller than the diameter of the cylinder. I'm going to use those assumptions to construct the fluid flow. And then I'm going to imagine adding a particle to the fluid, which is much smaller than the cylinder. And that'll legitimize my using these Maxey-Riley equations to particle dynamics. One doesn't need to do this computationally. In fact, the related problem of a fixed cylinder in a viscous flow that's oscillating back and forth at infinity has been considered in a sequence of papers that includes this paper due to Holtzmark et al. In the 1950s, where essentially they since A over D is small, they're able to use that as a small parameter and come up with an asymptotic expansion in powers of that parameter. So to one can adapt that solution to this problem where the fluid is fixed at infinity, but the cylinder is moving in a reasonably straightforward way. So here's a picture of the fluid velocity field that arises in that case. So this is just the upper right quadrant. In fact, there's a symmetry in this problem. So what happens is you get 4 quadrants that look like mirror images of each other. In the figure on the left, I'm showing the time-averaged Eulerian streamlines. Right? So this thing oscillates back and forth, and then I take the average fluid velocity at each point, and then these are the lines to which the average fluid velocity vectors are tangent. So these are the Eulerian streamlines. Okay, don't go away. These, on the other hand, are the Lagrangian streamlines. So these are the paths of fluid particles. And you see that they're different. So that difference is this Stokes drift that arises. Even in non-ideal fluids, there's this Stokes drift. Here's just another picture of that shows that, in fact, these streaming cells, there are separatrices. That, remember the movie with the filament in which we saw near the filament there was a circulatory cell in one direction, but outside that there was a complementary circulatory cell. So in fact that occurs in this model as well. Here's circulation this way, here's circulation that way. On the bottom, this is just a snapshot of the vorticity field in a simulation of this model that shows that the vorticity is largely confined to a Stokes layer that's thinner than the thickness of those circulatory cells shown at the top. The second example that I'll show you before we're finished is just a variation of the first example, where I consider 2 cylinders, and while one of them is oscillating, the other oscillates at twice that frequency. So this is a movie. So here's the cylinder. I've shown in light gray the time-averaged Lagrangian streamlines. So I'm not going to show the cylinder oscillating. I'm just assuming that I've sort of averaged the movie of the cylinder oscillating. You see these Lagrangian streamlines, and I've tagged several fluid particles here. So I'll let the movie run, and you'll see that the fluid particles, if they are fluid particles, meaning that they're neutrally buoyant, they ought to follow these Lagrangian streamlines, and this is done in Reynolds number. So if I do that, the fluid particles indeed follow these time-averaged Lagrangian streamlines. So the motion you see are stroboscopic pictures of the locations of these particles taken at the end of each oscillatory period. And then this is just one trajectory of one particle showing that if I don't average it, what's actually happening is the particles are oscillating as they follow these trajectories of the mean. So the time to make one excursion is of order 1 over A over D squared. So it's something like 100 oscillations to get one complete loop. So what if in that movie I replace my fluid particles with particles that are more dense than the fluid? Something interesting happens. So if I have particles that are heavier than the fluid, they actually get attracted to more or less the center of that Lagrangian streaming cell. Not exactly the center. They get attracted to a point inside that center. That's sort of a critical feature if you want to be able to attract fluid particles. In fact, the reverse happens if you have a lighter than fluid particle. So here are snapshots of particle trajectories, one for the case in which the particle density is neutral, and so the particle follows the Lagrangian streamline on average, one for which the particle density is greater than that of the fluid, and the particle is attracted to the center of the streaming cell, and then one in which the particle density is less than that of the fluid, and the particle spirals outward from the cell. This actually seemed briefly counterintuitive to me when I first saw this, because you think, I'm drawing this thing around in a circle, you'd expect the heavy thing to be thrown outward by centrifugal forces or something, and the lighter thing to be sucked inward. But in fact, that intuition is correct, but one needs to think about the motion of the particles relative to the streamlines. So here's how you can explain what's happening in these problems. Here's one particular Lagrangian streamline, and suppose I'm interested in determining whether a particle will be thrown outward or inward relative to that Lagrangian streamline. So I can measure the discrepancy between the velocity of this particle and the velocity tangent to the Lagrangian streamline by defining an angle alpha between the two. So if I define this angle alpha in terms of this cross product, so that here alpha is negative, but here alpha is positive, you can show that the rate at which alpha changes is proportional to a few things. It's, number one, it depends on a term having to do with the relative density of the fluid and the particle. So whatever happens for a heavy particle, the opposite should happen for a light particle. Number two, it depends on the velocity of the fluid. So whatever happens when you drive the fluid at one speed ought to happen more quickly if you drive the fluid more quickly. And then thirdly, and perhaps most interestingly, it depends on the curvature of the streamline. So one can see that what happens is that for a heavy particle is always thrown outward relative to the curvature of the streamline. So out here, if this particle is heavy, it has a tendency to fail to make the turn with the Lagrangian streamline. But in here, the same thing is true. If you look at the structure of the Lagrangian streamlines in these cells, you find that because of the greater density of these streamlines close to the body, relative to out of the body, that as the heavy particle is constantly crossing outward across these streamlines, and the definition of outward flips when it comes in here, and the curvature reverses, in the net, heavy particles sort of make their way inward over those level sets, whereas light particles make their way outward. So that's sort of a result, in the sense that if I want to know how to design a velocity field in order to capture or eject particles, all I really need to do is design the time average Lagrangian streamline structure, and then I can figure out where the particles will go just from looking at that streamline structure. So to illustrate that, here's example number 2. So this is 2 cylinders, and one of them is oscillating at twice the frequency of the other. So I've broken symmetry in that problem, so you can see the time average Lagrangian streamline structure is asymmetric. If I run the movie, so these are all particles heavier than the fluid, particles end up in various places in a way that's not necessarily intuitive without this interpretation in terms of Lagrangian streamlines. But it's actually possible to sort of predict which ones will end up where and which ones will end up trapped where. So this provides some sort of preliminary insight into how we should design placements and frequencies and amplitudes. I haven't mentioned amplitude, and the amplitudes of vibrations of these things in order to create trapping regions. I should stop, but let me just make 2 remarks about future work. So one thing I did not mention was the idea of changing the oscillatory frequency of a single cylinder during a run. So here's a result that shows if I vibrate a single cylinder at a certain frequency so as to attract a heavy particle to a certain trapping point, I can then double the frequency of oscillation, and that will move the trapping point. And so the particle will then be re-excited and moved to another trapping point. So changing frequencies, even in the 1-cylinder case, changes the geometry, if not the topology, of the streaming cell. So it's possible just to use 1 cylinder to capture particles and then move them around locally. But then, our real goal is to have multiple cilia and to do things like capture particles here, pass them over to this cilia. So here's a simulation in which first I oscillate the cilium on the left, capture a set of particles, then I stop the oscillations of the cilium on the left, I begin oscillations of the cilium on the right, and then very slowly, in fact, the cilium on the right, despite the distance, manages to steal these particles away from the motionless cilium. Eventually, by the end of the movie, 5 or 10 seconds from now, these particles are trapped around the cell. That's all I should say. Sorry for the late start. I realized. I guess I didn't talk as fast as I wanted.
When the particles in the cylinder was vibrating, how did we find the motion? Was it found exactly from the Stokes equations?
So in the case in which there was only 1 cylinder.
Only one vibrating.
So in the case in which there's only 1 vibrating cylinder, there's an analytical result that is a expansion in powers of the parameter epsilon, which represents the difference between the ratio of the amplitude to the size of the cylinder. So in using that expansion, I only consider movies in which that ratio is small. We also do, and for the two cylinders, I just have a high fidelity Navier-Stokes solver, a viscous vortex particle method solver to generate the fluid flow. So far we've been able to validate the analytical model using these computational simulations. It seems really
And for two cylinders, you emulated it numerically.
That's right. That's right. I don't know if it's possible to cheat that and somehow superpose in a mathematically not legitimate way the analytical solutions. Maybe. Possibly with this large separation.
So in the case of one cylinder, you just take a truncated series representation.
That's right. That's right. Order epsilon squared.
Another questions?
Can I ask you what frequency you are oscillating the cylinder?
Yeah, so in fact, there's a Reynolds number that we were using in parameterizing these things that has to do with the frequency of oscillation relative to the viscosity that we choose and the size of the boundary. So in all these simulations, it was somewhere between 0 and 100. Very.
And what software you are using to simulate these things? How you are modeling it?
Homemade software for training. Yeah.
So, could you comment again on the actual theoretical description? So you're actually solving the fluid flow around the oscillating cylinder.
That's right.
And you're coupling with the particles using these taxi relay equations.
That's right. So I assume that I obtain the fluid flow, and then I assume that the addition of particles will not change the fluid flow in any way. And I imagine that the fluid flow is now just a background force on the particle.
Okay. In the fluid flow, you basically solve by brute force direct simulations, or you're using some kind of fundamental solution for that? I didn't get that.
That was similar to his question. So in the single cylinder case, there is a series expansion solution that one can use, subject to some assumptions. But we also have just computational simulations.
That's fine. Thank you very much.
As far as I understand, you assume that Reynolds number for the cylinder is rather high because you have some boundary layer terms there. And for the particle, it is low.
I agree that there are different Reynolds numbers involved. I admit that I mentioned only this one, which, well, so A is assumed to be much less than D, right?
But you, when you have shown the equation of the particle, there was a term, integral differential term.
Yes.
That corresponds to the boundary layer.
Yes. Yes, and so one question when we began this was whether or not that term would be significant. So I have only computational results to say that
You included it or not?
we did include it, yeah. We had hoped that it would not be significant, because if it were not there, we could do averaging sorts of things in a very easy way to get analytical results. And that term is an obstacle. But based on the simulations, it seems that term is significant. And in fact, so that term, the so-called Bassett force term, Bassett himself, I think, was one of the first people to look at modeling particles moving in oscillating fluids like this far back into the 1800s. And so that term has been an obstacle for a long time.